I'm the makeshift Mr. Daycock, and today I'm going to be teaching you how to solve basic second-order differential equations. So here is an example of such a differential equation, and it looks quite complicated. We've got d2y by dx squared plus 7 lots of dy by dx plus 10 lots of y equal to 0. And this can come up in various situations. It can come up when you've got a damped pendulum or various other options. But basically, we want these combinations here to equal 0. Okay, so what we want to ask ourselves is, well, what we need to notice is we want these things to cancel out. We want the dy by dx to cancel out with the y's and to also cancel out with the d2y's by dx squared. So when we differentiate them, we want them to be the same. So what we really want to think is we want to try out y being equal to e to the x, because we want it to differentiate, and when we differentiate it, we want it to be the same. But actually, we don't know it's going to be exactly that. Now, I could take multiples of it, but actually that won't change anything, because when I differentiate a multiple, I end up with the same thing anyway. So what I'm going to do is I'm going to take multiples of the x, just to give it a little bit of variance, to go, well, what it could be something different. So I'm going to write it as y equals e to the alpha x, which is going to give me dy by dx is going to be equal to alpha e to the alpha x. And d2y by dx squared is going to be equal to alpha squared e to the alpha x. And this is kind of the key thing. Now let's substitute those in. So if I substitute those in, I'm going to get alpha squared e to the alpha x plus 7 lots of alpha e to the alpha x plus 10 lots of e to the alpha x. And of course that equals 0. But what we should notice is that in every term we've got this e to the alpha x. So I can factor that out. So I can get e to the alpha x lots of alpha squared plus 7 alpha plus 10 equal to 0. And now, to solve this, either e to the alpha x equals 0, which isn't possible, or alpha squared plus 7 alpha plus 10 has to equal 0. And this is possible. In fact, this is just a very simple factorizable quadratic. And so what we're going to get is alpha plus 5 alpha plus 2 equals 0, and that tells us that alpha is equal to minus 5 or alpha equals minus 2. Which then tells us my solutions are y equals e to the negative 5 alpha, negative 5x, plugging in alpha equals, going back to this original thing we tried, y equals alpha x minus 5x, or y equals e to the minus 2x. And we're done. Except not quite. Because the key thing here is, as I said before, differentiation is linear. So if I were to take any multiple of e to the minus 5 alpha, of minus 5x, or any multiple of e to the minus 2x, that would still work. And in fact, if I were to add them together, when we differentiate, you just differentiate each bit individually. So if I were to add them together, I would also have a solution. Hence, my general solution isn't these two particular ones, but it's actually any combination of them. So my general solution is y equals a, where a is some unknown, e to the minus 5x, plus b, where b is any other multiple unknown, e to the minus 2 x. And that is my general solution. And notice it has two unknowns. First order differential equations has one arbitrary constant. First order differential equations have one arbitrary constant, but second order differential equations can have two arbitrary constants. And here they are, a and b, two arbitrary constants for our general solution. So this is our general solution to such an equation. Now, I want you to notice something, because we don't need to put this much work in. This here was the key equation. It's called the auxiliary equation. And why is it so key? Well, it's key because we started with d2y by dx squared plus 7 lots of dy by dx plus 10 equals 0. And notice how the coefficients match up exactly. And this will always be the case. So if you have a differential equation with a y double dash, that's the second derivative of y, plus b y dash, that's the first derivative of y, so you know dy by dx, plus c y equals 0, then it will always have auxiliary equation a alpha squared plus b alpha plus c equals 0. Always. And then all you need to do is solve this quadratic, and that gives you your general solution. And so therefore it will always have general solution of y equals a e to the first root of this, so alpha 1 x plus b e to the alpha 2 x, where alpha 1 are the roots of this equation. Alpha 1 and alpha 2, sometimes called alpha and beta, are the roots of this auxiliary equation. Okay, so let's use that in action. Let's use that little trick there we've got in action. Here's find the general solution of this, which is exactly the same as the one I had before, because my copy and paste didn't work properly. It's meant to be minus 8 minus 20y. So we have d2y by dx squared minus 8 dy by dx minus 20y equals 0. And we can jump straight to the auxiliary equation. The auxiliary equation must be, well, our first coefficient is 1, so it's just going to be alpha squared. Our second one is minus 8, so it's going to be minus 8 alpha. And then our third one is minus 20 equals 0. And this just factorizes, so we're going to get alpha minus 10, alpha minus plus 2 equals 0, and that gives us alpha equals 10 or alpha equals negative 2, and therefore that gives us the general solution of y equals a e to the 10x plus b e to the negative 2x. And there you go. You can solve these as quickly as that, so long as they are of the form some amount of d2y by dx squared plus some amount of dy by dx plus some amount of y equal to 0. We will be moving on to more complicated examples, and there are a few caveats we have to cover first in regards to these ones, but that is our general principle. Okay, thank you very much for watching, and I'll see you in the next video.